We spend our lives fighting against endings. From the smallest moments to the grandest sagas, we cling to what is, fearing the blank slate, the final curtain, the ultimate silence. But what if the end isn't something to be feared at all? What if, after eons of creation, after trillions of years of light and life and fury, the final act of the cosmos is not a sudden, violent punctuation, but a long, slow, and profoundly beautiful fade to black? This isn't a story to ignite your fear. Instead, I want to invite you on a journey to the very edge of existence, to witness the most epic, majestic, and profound story of all, the life cycle of the cosmos itself. For everything that has a beginning must eventually have an end. Our universe is no exception. And the incredible thing is, we tiny, fleeting beings on a pale blue dot already have a pretty good idea of how it's all going to go down. Think of it like this. We're not just stargazers anymore. We're cosmic meteorologists. We've gathered the universe's most crucial weather data. Things like dark energy, the relentless march of entropy, the accelerating expansion of space itself. And with this data, we can peer trillions of years into the future, sketching out the ultimate cosmic weather forecast. This isn't about predicting a storm that threatens us. This is about stepping back, removing our brief, precious moment from the equation, and simply witnessing the inevitable, magnificent conclusion to the greatest story ever told. So, let's open that forecast. Let's look at the ultimate horizon, the most likely scenario, the one supported by the strongest evidence we have today, is often called the heat death, or the big freeze. It's not dramatic in the way a Hollywood blockbuster might imagine. It's far more subtle, far more profound in its quiet inevitability. Imagine a universe that just expands forever. Right now, as you listen to my voice, the universe is getting bigger every second, and it's doing so at an accelerating rate. This isn't because of some inherent momentum from the Big Bang anymore. No, this accelerating expansion is being driven by a mysterious, repulsive force that cosmologists have dubbed dark energy. It's an invisible, enigmatic entity that makes up a staggering 68–70% of the total mass energy content of our universe, and it began its accelerating push about 5 billion years ago. It's like an unseen hand, gently but firmly, pulling everything further and further apart. In the heat death scenario, dark energy continues its relentless work. Galaxies will drift so far apart that the light from one will never reach another. The night sky, currently a glittering tapestry, will become an inky, featureless black. The universe will become colder, darker, and emptier. It's the ultimate victory of the second law of thermodynamics, a concept first given shape by minds like Lord Kelvin in the 19th century. Entropy, the universe's inherent tendency towards disorder, will reach its maximum, a state of perfect, unchangeable equilibrium. Picture this. Eons pass. Trillions of years melt away like moments. The brightest stars, the massive, brilliant blue giants, will have long since exhausted their fuel and collapsed into neutron stars or black holes. Even our own sun, a middle-aged yellow dwarf, will have swelled into a red giant, consumed Earth, then faded into a white dwarf, eventually cooling into a dark, dense cinder. But even the smaller stars, the long-lived red dwarfs, the cosmic embers that burn with frugal efficiency, will eventually flicker out. These stellar marathon runners are expected to burn for trillions of years, far longer than the current age of the universe. But one day, even the last red dwarf, the final beacon of starlight in a universe plunged into eternal night, will sputter and die. Imagine that moment, the universe's last light extinguishing. A profound, immense darkness settles, a silence so deep It would swallow the concept of sound itself. What's left then? Mostly stellar remnants, cold planets, and an increasingly thin soup of fundamental particles. But even these aren't forever. The black holes, those cosmic leviathans, are next on the chopping block. For the longest time, we thought black holes were eternal, cosmic prisons from which nothing, not even light, could escape. But then, in 1974, a brilliant mind named Stephen Hawking revolutionized our understanding. He theorized that black holes aren't entirely black. Through a bizarre quantum mechanical process, now known as Hawking radiation, they slowly but surely leak energy. It's an almost imperceptibly slow process at first. A black hole with the mass of our Sun would take an estimated 10⁻⁻⁶7 years to completely evaporate. That's a 1, followed by 67 zeros, a number so vast it makes the current age of the universe look like a blink. But the supermassive black holes, those titans at the centers of galaxies, weighing billions of times the Sun's mass, they could take up to 10⁻100 years, or even an astonishing 10⁻160 years, to finally wink out. Visualize this: an animated data visualization, stretching across an unimaginable canvas of time. A supermassive black hole, shrinking ever so slowly, for quadrillions upon quadrillions of years. It's almost imperceptible, a cosmic weight loss program on an epical scale. But then, as it gets smaller, the rate of evaporation accelerates. It shrinks faster and faster, until in its final moments, it erupts in a blinding, brilliant flash of gamma rays. The last major event in the universe, a final defiant gasp of energy before it, too, is gone. And then, what? Even after the stars are gone, after the black holes have evaporated, what remains of matter itself? This brings us to an even more speculative, yet profoundly significant possibility: proton decay. It's a hypothetical process, predicted by some grand unified theories, where the very protons that make up atoms, the bedrock of all matter as we know it, might eventually decay into lighter subatomic particles. If this theory holds true, then after all the cosmic fire and fury, after the long, slow death of light and gravity, even the atoms themselves will dissolve, leaving nothing but a cold, thin soup of photons, electrons, and neutrinos, drifting endlessly apart in an ever-expanding, perfectly dark, perfectly empty void. This is the ultimate, but wait, it gets emptier moment. The soundscape of this heat death would be astonishing. We begin with the vibrant music of the cosmos, the hum of nebulae, the roar of supernovae. As light fades, so too would the higher frequencies. The heat death would be characterized by an ultra-low frequency hum, almost felt more than heard, a cosmic thrum that slowly, imperceptibly, fades into absolute perfect silence, an eternal quiet. But what if the universe doesn't fade so gently into that good night? What if its end is far more dramatic, far more violent? Physics, ever the creative storyteller, offers us a few more visceral possibilities. Enter the Big Rip. This is the cosmic equivalent of turning the volume up to 11, then breaking the knob off. In this scenario, dark energy isn't just gently pushing things apart. Its repulsive force grows stronger and stronger, accelerating the expansion of space with such ferocity that it eventually overcomes all fundamental forces. Imagine a POV sequence. You're standing on a planet, gazing up at a familiar night sky. Suddenly, the galaxies in the distance begin to stretch, becoming impossibly long, wispy threads, before tearing apart entirely. Then, closer to home, your own galaxy, the Milky Way, starts to distort. The stars, once held together by gravity, begin to fly off into the void. The moon, once a constant companion, is ripped away from your planet. Then your planet itself, unable to withstand the accelerating expansion of space within it, begins to stretch and disintegrate. Mountains rise and fall like ocean waves. The ground beneath your feet buckles and tears. Finally, the very atoms that make up your body, the very forces that bind your cells, your molecules, your protons and electrons together, are overcome. You are atomized, dissolved into a sea of fundamental particles, which themselves are then torn apart. A terrifying, visceral, and instantaneous end. The sound, a deafening cosmic tearing, like the fabric of reality itself being shredded, or perhaps the universe's story ends with a big crunch. This is the reverse of the Big Bang, a cosmic retraction rather than an endless expansion. In this scenario, gravity, the great sculptor of the cosmos, eventually wins. Instead of dark energy dominating, the total mass and energy density of the universe would be enough to halt the expansion and pull everything back in. Think of it like throwing a ball into the air. It flies upward for a while, but eventually, gravity pulls it back down. In the Big Crunch, the universe, having expanded for billions of years, would reach a maximum size, pause for a cosmic instant, and then begin to contract. Galaxies would rush towards each other, colliding in spectacular, furious bursts of energy. Stars would merge, space would heat up, and the cosmic background radiation would grow hotter and hotter, brighter and brighter. Everything would collapse back in on itself, squeezing all matter and energy into an infinitely dense, infinitely hot singularity, the very state from which it all began. The sound of a big crunch would be a terrifying, accelerating crescendo, a cosmic scream as all of existence is crushed back into nothingness. The idea of an expanding universe, the very foundation of these end scenarios, wasn't always obvious. It was the brilliant Russian mathematician Alexander Friedmann who, in 1922, first developed equations describing a dynamic, expanding universe based on Einstein's general relativity. Then, in 1927, a Belgian priest and physicist, Georges Lemaitre, independently proposed that the universe was expanding and originated from a single point, his primeval atom, which we now call the Big Bang. And just a couple of years later, in 1929, the American astronomer Edwin Hubble provided the undeniable observational proof, showing that galaxies were indeed moving away from us, and the farther they were, the farther they receded. This discovery of cosmic expansion was a monumental turning point, laying the groundwork for all our modern cosmological models and our predictions for the universe's ultimate fate. There's even a more speculative, truly bizarre possibility called vacuum decay. Imagine that the very fabric of space, the vacuum itself, isn't as stable as we think it is. What if it's currently in a false vacuum state, like a ball resting precariously on a high shelf, waiting to drop to a lower, more stable shelf? If a quantum bubble of a different, more stable kind of space were to spontaneously form somewhere in the universe, it could expand at the speed of light, destroying everything in our current universe as it goes, rewriting the laws of physics in its wake. A sudden, unannounced, and utterly absolute end. So here we stand, at the precipice of unimaginable timescales and profound cosmic goodbyes. We've looked at the scientific inevitability of an end, not as a threat to us, but as the natural final chapter in the universe's grand story. We've peered into the ultimate forecast, seeing the slow, quiet fade of heat death, the violent tearing of the Big Rip, and the crushing embrace of the Big Crunch. But if all of this is true, if the universe, in all its majestic glory, is destined for an end, whether it's a whisper or a scream, what does that mean for our brief, shining moment within it? What does it say about us? This isn't a call to despair. Far from it. This journey to the end of everything isn't about insignificance. It's about ultimate perspective. It's about understanding the profound value of the present moment. In a cosmos destined to dissolve into cold emptiness, or to be torn asunder, or to be crushed into oblivion, the fact that we exist at all, that there is light and life and consciousness, is the most improbable, most precious thing imaginable. Our time, the era of stars and galaxies, of complex chemistry and self-aware beings, is but a fleeting instant in the cosmic calendar. It's a brief, improbable window when the universe is alive and aware of itself, through us, through our curiosity, our science, our art, our love. We are the universe experiencing itself, trying to understand its own story. From its fiery birth to its inevitable farewell, the legacy of humanity, in the face of such cosmic finality, isn't found in permanence. It won't be in structures that last forever, or information that survives the evaporation of black holes. No. Our meaning, our profound contribution, lies in the experience itself, in the brief, improbable, beautiful act of existing, in the conscious observation of reality, in the connections we forge, in the knowledge we uncover, and in the awe we feel. Scientists like Edwin Hubble, Georges Lemaitre, Stephen Hawking, and contemporary voices like Dr. Katie Mack, who tirelessly explore these profound questions, are not just presenting facts. They are anchoring us in this incredible story, highlighting the ingenuity and relentless curiosity of humanity. They show us that even in the face of the ultimate end, our quest for understanding, our human passion, is a magnificent act of defiance against the void. So when you look up at the night sky now, knowing what you know, does the vastness feel different? Does the fleeting beauty of a shooting star, or the steady glow of a distant galaxy, hold a new kind of preciousness? If our universe is a grand symphony with a definitive final movement, does that make the music playing right now all the more vibrant, all the more essential? Thank you for joining me on this journey into the ultimate forecast. If this cosmic perspective has opened your mind, sparked your curiosity, or simply left you awestruck, then I invite you to subscribe to Celestial Enigmas. Together, we'll continue to explore the universe's most profound mysteries, one enigma at a time. We spend our lives fighting against endings. We cling to moments. We resist goodbyes. And we build legacies meant to outlast us. But what if the end is the most natural thing in the universe? What if, after trillions of years of light and life and fury, the final act of the cosmos is not a bang, but a long, slow, and profoundly beautiful fade to black? Here on Celestial Enigmas, we've journeyed through the universe's most breathtaking mysteries, from its explosive birth to the secrets hidden within its darkest corners. Now, as our first season draws to a close, we turn our gaze to the ultimate enigma. How will it all end? This isn't a story of fear. It's a story of ultimate perspective, a poetic and majestic farewell to the cosmos itself. Imagine, if you will, the universe as a magnificent, roaring bonfire. For billions of years, it has blazed with unparalleled intensity, fueled by vast clouds of cosmic gas, giving birth to generations of stars and galaxies. We, in our brief, shining moment, are living in the age of its brilliant light. This is the age of stars, a cosmic summer where new suns are born, planets form, and life, against all odds, takes root. But like any fire, no matter how grand, its fuel is final, the most probable fate for our universe. The scenario scientists call heat death, or the Big Freeze, describes a cosmos that simply runs out of steam, slowly cooling and darkening until it becomes an empty, eternal void. This isn't an abrupt stop, a sudden blackout. Oh no. This is a process of immense, almost unimaginable slowness, a cosmic exhalation that will unfold over timescales that dwarf our current 13.8 billion years into a mere blink. It's a slow, majestic fade, a final ghost-like dance before the true emptiness. The universe, in essence, achieves a state of perfect, unchanging equilibrium, maximum entropy. It's not a dramatic destruction, but rather a quiet resignation. Right now, in our present moment, the universe is still bursting with activity. Galaxies spin, nebulae glow, and stars fuse hydrogen into helium, showering their surroundings with light and heat. This vibrant activity is powered by the available energy, the fuel of our cosmic fire. We know, thanks to incredible scientific breakthroughs, that our universe is expanding. And not just expanding, but accelerating in its expansion. This acceleration, a discovery made in 1998 that earned its discoverers a Nobel Prize, is driven by a mysterious force we call dark energy. This enigmatic entity, which we can't see or directly detect, is estimated to make up a staggering 68 to 70% of the total mass energy content of the universe. It's the engine behind the expansion, pushing galaxies apart at an ever-increasing rate. We've even measured this rate, known as the Hubble constant, to be around 74 kilometers per second per megaparsec. Though there's a fascinating, persistent discrepancy in measurements that scientists call the Hubble tension. This accelerated expansion, driven by dark energy, began roughly 5 billion years ago, setting the stage for the universe's long, slow decline. But the fire, as brilliant as it is now, is already consuming its kindling. In the cosmic long view, the hydrogen gas, the primordial fuel for new stars, is slowly but surely being used up. Eventually, countless eons from now, the grand nurseries of stars, the nebulae that paint our night sky with such vivid colors, will go dark. There will be no more fresh gas to ignite, no more new suns to be born. The age of brilliant, massive stars will pass. The universe will stop creating new light. This marks the beginning of the age of embers, the true focus of our journey today. As the cosmic fire dims, the universe will be left with its remnants, its dying coals. These embers are the stellar corpses that remain after their fiery lives. We're talking about white dwarfs, neutron stars, and stellar mass black holes. Take our own sun, for example. In about 5 billion years, it will swell into a red giant, then shed its outer layers, leaving behind a glowing, super-dense core about the size of Earth. This is a white dwarf. It's incredibly hot at first, but with no more nuclear fusion happening, it will slowly, inevitably, cool down. Imagine a white-hot piece of coal gradually fading to a dull red, then to black. That's the fate of a white dwarf. It will radiate its remaining heat into the vastness of space for trillions upon trillions of years, becoming a black dwarf, a theoretical, utterly cold, dark, stellar cinder. We haven't observed any black dwarfs yet, because the universe simply isn't old enough for even the first white dwarfs to have cooled completely. But they are coming. For stars far more massive than our sun, their endings are more dramatic. When they exhaust their fuel, they collapse violently, exploding as supernovae. What's left behind depends on their initial mass. If the core is dense enough, but not too dense, it collapses into a neutron star, an incredibly compact object where protons and electrons are crushed together to form a sea of neutrons. A single teaspoon of neutron star material would weigh billions of tons. These are like ultra-dense, super-fast spinning embers, still radiating some energy, but again, destined to slowly cool and fade. And then, for the most massive stars, the collapse is so complete, so utter, that nothing can stop it. They form stellar mass black holes, regions of spacetime, where gravity is so intense that not even light can escape. These are the deepest, darkest embers of all, swallowing light and information, seemingly eternal. So, in this degenerate era, the universe won't be completely dark. It will be a dim, eerie landscape, punctuated by the faint, cooling glows of white dwarfs, the occasional flicker from a neutron star, and the invisible gravitational presence of black holes. The immense distances between these objects will continue to grow as dark energy relentlessly pushes the fabric of space apart. The universe will become a vast, cold museum of dead star. But here's the aha moment. Within this long, slow decay, the end isn't an abrupt stop. Even in this incredibly sparse, dark cosmos, things will still happen. Over unimaginably long timescales, the gravitational whispers of these stellar corpses will still interact. Imagine rogue white dwarfs, neutron stars, or even black holes drifting through the galactic graveyard. Every now and then, perhaps once in a googol of years, two of these dead stars might collide. These wouldn't be the star-forming, galaxy-shaping collisions of our current era. No, these would be rare, spectacular, ghost-like dances, a final brief flash of light as two white dwarfs merge, igniting a supernova that briefly illuminates the darkness, a cosmic swan song, or two neutron stars spiraling into each other, creating ripples in space-time and a burst of high-energy radiation, a final faint echo of the universe's earlier fury. These collisions would be incredibly rare, isolated events, like distant dying fireflies in an otherwise infinite night. But for a fleeting moment, they would break the profound monotony, reminding us of the universe's past vibrancy. And then, there are the truly long-lived stars, the tiny, unassuming red dwarfs. These stars are the tortoises of the cosmic race, burning their nuclear fuel with incredible efficiency and at a glacial pace. Our sun, a yellow dwarf, will live for roughly 10 billion years, but a red dwarf, with just a fraction of the sun's mass, can shine for trillions of years. We're talking about timescales so vast, they make the current age of the universe look like a newborn snap. These are the last sputtering flames of our cosmic bonfire. Imagine, if you can, a universe 100 trillion years from now. Most of the white dwarfs have cooled to blackness. The neutron stars are silent. Black holes are still there, vast and mysterious. But somewhere, in the unimaginable darkness, there is a tiny, persistent glow. It's a red dwarf, the last star in the universe, still valiantly fusing hydrogen, albeit with a faint, ruddy light. This is the last light. For billions more years, it will continue its lonely vigil, its feeble light barely piercing the gloom. And then, it too will exhaust its fuel. Its nuclear furnace will finally die. That last persistent glow will dim, then flicker, and then, with an immense, profound sigh, it will extinguish. The universe will be plunged into an almost absolute darkness, a cold, empty void, punctuated only by the faint, theoretical glow of evaporating black holes. This brings us to the most enduring, most mysterious of these cosmic embers: black holes. For a long time, black holes were thought to be truly eternal, cosmic prisons from which nothing, not even information, could ever escape. But then, in 1974, a brilliant mind named Stephen Hawking revolutionized our understanding. He theorized that black holes are not entirely black. Through a mind-bending quantum mechanical process, they slowly leak energy. This phenomenon, now known as Hawking radiation, means that black holes aren't permanent. They shrink, they radiate, and eventually they evaporate. Think about that for a moment. Even the universe's ultimate gravitational traps, its deepest voids, are not eternal. They are temporary. This process, however, is unbelievably slow. A black hole with the mass of our Sun would take an estimated 1067 years to completely evaporate through Hawking radiation. To put that into perspective, the current age of the universe is a mere 1.38 10 to 10 years. We're talking about a number with 67 zeros after it. It's a timescale so vast it beggars the imagination. Supermassive black holes, the behemoths found at the centers of galaxies, with masses billions of times that of the Sun, would take even longer, up to 10,100 years, or even 10,106 years, to fully evaporate. Visualize this: a supermassive black hole sitting at the center of a now empty galaxy. For eons upon eons it grows, absorbing what little matter drifts its way. But as the universe expands and empties, its fuel runs out. Then the slow, imperceptible shrinking begins. For most of its immense lifespan, it would appear utterly static, unchanging. But over these mind-boggling timescales, it would shrink, imperceptibly at first, then faster and faster, as its mass decreases and its radiation rate increases, and then, in its final moments, as it reaches a critical tiny mass, it would explode in a brilliant final flash of gamma rays. This would be the last major event in the universe, the ultimate cosmic fireworks display, marking the end of the last, most powerful embers. But wait, it gets emptier. After all the stars die, after all the black holes evaporate, what's left? A cold, dark, incredibly thin soup of elementary particles, photons, neutrinos, electrons, and positrons, drifting almost infinitely far apart. Here's a concept that is truly mind-bending, and for most viewers, a surprising reveal: the proton decay moment. You see, the very protons that make up all ordinary matter, you, me, the Earth, the remaining electrons and positrons, might not be eternal either. This is a hypothetical process predicted by some grand unified theories, or GUTs, ambitious frameworks in physics that attempt to unify all the fundamental forces of nature, except gravity. If these theories are correct, protons, those seemingly stable building blocks of existence, could decay into lighter subatomic particles, like positrons and neutral pions, which would then quickly decay into photons and other leptons. This isn't something we've ever observed, and experiments have set incredibly long lower limits on its half-life. Theoretical models constrain its half-life to be at least 1.7 x 10 to 34 years. Again, a number so large it's almost meaningless. But if it does happen, if protons do decay, then it means that all matter as we know it will eventually dissolve. The very atoms that compose us, the planets, the remnants of stars, everything will simply cease to exist as coherent structures. It would be the ultimate deconstruction, a final unraveling of reality itself into a sea of light particles and other fundamental quanta. This is the ultimate. But wait, it gets emptier moment. After the stars are gone, after the black holes have faded, if proton decay occurs, even the last vestiges of solid matter would melt away. The universe would truly become nothing but an incredibly diffuse, cold, thin soup of fundamental particles spread out across an ever-expanding, ever-emptier void. The concept of maximum entropy would be fully realized. No more energy gradients, no more differences, no more potential for anything to happen. Just an eternal, unchanging dark and silent uniformity. This is the dark era. Imagine that profound darkness, that absolute silence. The sound of the universe dying in this scenario isn't a bang or a whimper, but the slow, agonizing fade to utter quiet. We started with the music of the cosmos, the vibrant hum of creation. Now, it has faded into an ultra-low frequency thrum, an almost imperceptible vibration of the vacuum, before finally dissolving into an absolute perfect silence. The heat death isn't violent. It's not a dramatic collapse or a sudden rip. It's a gentle, drawn-out process, a cosmic letting go. It's the universe achieving a final, perfect state of equilibrium and peace. A slow, majestic fade to eternal silence after trillions and googles of years of cosmic fury. It is perhaps the most tranquil, yet most profound, of all possible endings. But what if the universe doesn't choose such a quiet farewell? What if its final act is not a gentle fade, but a terrifying cataclysmic crescendo? What if, instead of slowly cooling, it's ripped apart or crushed back into nothingness? The universe, in its vastness, holds other, more dramatic possibilities for its ultimate conclusion, scenarios that are far from tranquil. And so, we find ourselves on the precipice of an unimaginable future, gazing into the profound stillness of the heat death. But before we journey to those other, more violent cosmic farewells, let's truly linger for a moment on the absolute finality of that slow fade. Let's really see the universe take its very last breath, stretching the concept of an ending beyond anything our human minds can comfortably grasp. Because even within the quietude of the heat death, there are events so epical, so mind-bendingly distant, that they redefine what empty truly means. Imagine, if you can, a cosmos where the last stars have long since flickered out. We're not talking about our sun, which has a lifespan of billions of years, but the truly hardy veterans of the stellar nursery, the red dwarfs. These celestial embers are the ultimate slow burners, tiny, dim, and incredibly efficient. They fuse hydrogen into helium at a glacial pace, conserving their fuel for an eternity compared to their brighter, more flamboyant cousins. Our sun will run out of hydrogen in about 5 billion years, but these cosmic marathon runners, they could keep going for trillions of years. Trillions. To put that in perspective, the universe as we know it has only existed for about 13.8 billion years. These red dwarfs will outlive countless generations of galaxies, witness the birth and death of civilizations beyond our wildest dreams, and still be humbly shining long after everything else has vanished into the deep. Picture one now, millions of trillions of years from today. It's barely a flicker, a faint ruby glow against an expanse of absolute black. Its light, once a beacon, now struggles to pierce the immense, ever-expanding void. There are no other stars nearby, no galaxies, because dark energy, that mysterious repulsive force that makes up an estimated 68–70% of the total mass energy content of the universe, has driven them so far apart that their light can no longer reach each other. The accelerated expansion, which cosmologists estimate began roughly 5 billion years ago, has won. Space itself has stretched and thinned, diluting everything, scattering the remnants of cosmic history across an infinite canvas of nothingness. And then, that last red dwarf too exhausts its fuel. Its core, no longer able to sustain fusion, contracts. The faint glow dims, then fades. The very last star in the universe goes out. Silence and absolute, profound darkness for unimaginable epochs. This is the state of the cosmos. A cold, thin soup of scattered particles, electrons, positrons, neutrinos, and the mysterious dark matter, endlessly drifting through an ever-expanding emptiness. The universe has reached its maximum entropy, a state of perfect disorder where no useful energy remains. The heat death isn't about everything getting hot. It's about everything becoming the same temperature, an utterly uniform, icy zero, where no work can be done, no processes can occur. It's the ultimate thermal equilibrium. But wait, there's still something left. The grand, silent behemoths of gravity, black holes. These cosmic singularities, once the engines of galactic centers and the remnants of massive stars, are perhaps the most enduring structures in the universe. They seem, at first glance, like eternal prisons of spacetime, trapping everything, even light, within their event horizons. For eons, they will be the most significant objects, the last bastions of order in a universe sliding into chaos. Yet, even black holes are not immortal. And this, my friends, is where the universe reveals its most meticulous, most patient secret, the phenomenon of Hawking radiation. This isn't just a fascinating theory. It's the universe's ultimate act of cosmic bookkeeping. How does this cosmic bookkeeping work? It's a bit mind-bending, but bear with me. The vacuum of space isn't truly empty. It's a seething, frothing quantum foam, constantly giving birth to pairs of virtual particles and antiparticles. These pairs pop into existence, exist for a fleeting moment, and then annihilate each other, returning the borrowed energy to the vacuum. It's a cosmic dance happening everywhere, all the time. But what happens when one of these virtual particle pairs pops into existence right at the edge of a black hole's event horizon? Sometimes, one particle, say the negative energy particle, falls into the black hole, while its partner, the positive energy particle, escapes into space. When the negative energy particle falls in, it effectively subtracts energy from the black hole itself. The black hole loses a tiny bit of its mass, and consequently, a tiny bit of its gravitational pull. The escaping positive energy particle is what we observe as Hawking radiation. It's an incredibly slow process, almost imperceptible at first. For a black hole with the mass of our Sun, the evaporation time is an estimated 10 to the 67th years. Let that number sink in. That's a 1 followed by 67 zeros. The current age of the universe is a mere 1.38 x 10 to the 10th years. We're talking about timescales that make the age of the universe seem like a blink. And for the truly gargantuan supermassive black holes, those cosmic leviathans found at the centers of galaxies with masses billions of times that of the Sun, the evaporation takes even longer. We're talking up to 10 to the 100th years, or even 10 to the 106th years. This is the realm of the Google years, a number so absurdly vast that it serves as a conceptual barrier for our linear human brains. There is no analogy, no comparison, that can truly make this timescale comprehensible. It is simply profoundly eternal to us, but the process, no matter how slow, is inexorable. Over these unimaginable eons, these black holes will slowly, steadily shrink. The smaller a black hole gets, the stronger the Hawking radiation it emits, and the faster it evaporates. It's like a cosmic ice cube slowly melting. But the smaller it gets, the faster it melts. And then, the moment arrives. After eons of patient cosmic bookkeeping, the debt is nearly paid. A black hole, perhaps one with the mass of a small asteroid now, having shed almost all of its immense mass, reaches its critical final moments. Its evaporation rate accelerates exponentially. In a fraction of a second, the remaining mass energy of the black hole is converted into a brilliant final burst of Hawking radiation. A dazzling, furious flash of gamma rays. This, my friends, is potentially the very last significant event in the universe. A final, brilliant, spectacular cosmic fireworks display. A single blinding flash of light, erupting from the vacuum. A triumphant roar of energy as the universe finally balances its books and reclaims every last joule of energy it ever lent to create these gravitational titans. After this ultimate light show, the black hole is gone. Nothing but a memory, a ripple in the fabric of space-time that quickly smooths itself away. And then, the universe gets even emptier than you imagined. Because even after the stars have burned out, and even after the black holes have evaporated in their final brilliant flashes, there's still one more layer of dissolution, one more step towards ultimate emptiness that physics speculates about: proton decay. If these theories are correct, then protons, over truly immense timescales, would eventually decay into lighter subatomic particles, like positrons and neutral pions, which would then quickly decay into photons, particles of light, and other even more ephemeral particles, like neutrinos. We've never observed a proton decay. Scientists have conducted experiments, shielding detectors deep underground from cosmic rays, watching billions upon billions of protons for years, hoping to catch just one in the act. So far, nothing. This non-observation tells us that if proton decay does happen, its half-life must be incredibly long, at least 1.67 x 10 to the 34th years. Again, a number that dwarfs the age of the universe by a staggering margin. Think about that. No more atoms, no more hydrogen, no more helium, no more carbon, no more oxygen. The fundamental structures that give rise to everything we call matter will cease to exist. They will simply unspool, dissolving into a thin, cold soup of light particles, photons, and neutrinos, and perhaps some dark matter particles, endlessly drifting through the ever-expanding void. This is the true ultimate emptiness. Not just a universe without stars or galaxies, but a universe without matter. No structures, no forms, no potential for anything to ever interact or cohere again. Just an infinitely dilute, infinitely cold, silent ocean of fundamental particles moving further and further apart, forever. The very concept of things disappears in this ultimate frigid vacuum. After trillions upon trillions of years of cosmic activity, the universe has finally, truly, achieved its final state. It's a state of perfect, absolute equilibrium. Nothing is happening. Nothing can happen. There's no energy differential to drive any process, no matter to form any structure, no force to bring anything together. Just the endless expansion, carrying the last lonely particles further and further apart into an eternal, featureless dark. What does it mean for us, then, to exist in this brief, shining moment, a fleeting instant when the universe is alive, vibrant, and, through us, aware of itself? It makes our present, our now, an improbable miracle, a precious anomaly in an otherwise endless, silent cosmic night. The beauty of this ending isn't in its despair, but in the profound appreciation it instills for the vibrant, improbable now. Okay, so we've talked about the quiet, almost gentle fading away. The universe, a grand old star, slowly dimming, settling into an eternal, featureless dark. That's the heat death, a poignant, majestic farewell that truly humbles the notion of existence. It's a vision of peace, a profound quiet, after an unimaginable symphony. But what if the universe doesn't choose a quiet exit? What if, instead of a slow, graceful bow, it's destined for a violent, cataclysmic crescendo? What if the final act of the cosmos isn't a long, slow fade to black, but a dramatic, terrifying tear, or a crushing, fiery collapse? You see, the universe, our cosmic home, is a dynamic, living thing, and its ultimate fate is far from a settled fact. It's an ongoing, thrilling mystery, one that hinges on some of the most enigmatic forces and numbers in all of physics. And as we peer into the deepest recesses of theoretical cosmology, two other profoundly dramatic endings emerge from the equations: the Big Rip and the Big Crunch. These aren't just scientific theories. They are cosmic dramas of unimaginable scale, each painting a picture of an end so utterly different from the heat death that it forces us to reconsider everything we thought we knew about finality. To really get a handle on these cosmic goodbyes, let's use a little visual aid, something that helps us grasp the immense forces at play. Imagine, if you will, our entire observable universe as the surface of a balloon, not just any balloon, but a cosmic balloon, with galaxies, stars, and planets, even you and me, represented as tiny, intricate patterns of ink painted onto its elastic skin. Now, you've heard us talk about the universe expanding, right? Well, this balloon is always being inflated, and the way it gets inflated, the forces that govern that inflation, will decide everything. Let's start with the first violent alternative, the Big Rip. This is the scenario where the universe's expansion doesn't just continue, it utterly loses control. It becomes a runaway freight train, accelerating faster and faster, driven by an almost unimaginable cosmic engine. What's driving this frantic, ever-increasing expansion? It's that mysterious, elusive force we call dark energy. Remember how we've talked about it before? Dark energy is like the universe's own anti-gravity. It's not just pushing things apart, it's pushing them apart with increasing ferocity. Scientists estimate that this enigmatic force makes up a staggering 68 to 70% of the entire mass energy content of the universe. Think about that. Nearly 3/4 of everything that exists is this invisible, untouchable, yet profoundly powerful entity. We can't see it, we can't touch it, but we can measure its effects. And its effects are, quite literally, tearing the cosmos apart. The discovery of this accelerating expansion, back in 1998, was a monumental moment in science. Two independent teams of astronomers, peering out at distant supernovae, found something utterly unexpected. The universe wasn't just expanding, it was speeding up. It was as if someone had pressed the accelerator on our cosmic balloon, and it's been picking up speed ever since. This discovery completely reshaped our understanding of the universe's ultimate fate, making scenarios like the heat death, and especially the Big Rip, far more plausible than they had ever seemed before. It even earned the leaders of those teams the Nobel Prize in Physics in 2011. Now, if this dark energy continues to behave in a particular way, if its repulsive force only grows stronger and stronger over time, then our cosmic balloon isn't just inflating, it's being stretched beyond its breaking point. Imagine that balloon, those intricate ink patterns of galaxies and stars and planets being pulled tauter and tauter. At first, the expansion just pushes galaxies away from each other, making the voids between them wider and emptier. That's what we see happening now. But in the Big Rip, this force becomes so overwhelmingly powerful that it overcomes everything. First, gravity loses its grip. Galaxy clusters, those magnificent cosmic cities, where thousands of galaxies are bound together in a gravitational embrace, would be ripped apart. Individual galaxies, like our own Milky Way, would then start to disintegrate. The stars within them, once held in elegant spirals and elliptical formations, would be flung out into the rapidly expanding void, each one accelerating away from its neighbors, becoming utterly alone in an ever-thinning cosmic soup. Then, the stars themselves would begin to feel the strain. Solar systems like our own would be next. Imagine our sun, its planets, its moons, held in a delicate gravitational dance for billions of years. In a Big Rip scenario, the very fabric of spacetime within our solar system would be stretching so violently that the sun's gravitational pull would no longer be enough to hold us. The Earth would be torn from its orbit, spiraling outward, away from its star, into the rapidly expanding darkness. Our moon, a constant companion for eons, would be ripped from Earth's embrace, and then it gets truly personal. Imagine you are standing on a planet, watching this cosmic horror unfold. At first, it's just the stars in the night sky, slowly receding, dimming, vanishing one by one as they're pulled away into the expanding abyss. Then, the galaxy itself begins to distort, its beautiful spiral arms stretching into long, impossibly thin streamers of light, before snapping like cosmic rubber bands. The sky, once a tapestry of billions of suns, becomes a canvas of frantic, accelerating emptiness. As the rip intensifies, the very atoms of your planet, of your body, would begin to feel the strain. The gravitational force holding the planet together would be overwhelmed. Mountains would crumble. Oceans would boil away. The planet itself would swell and deform, its solid rock stretching and tearing like taffy. Then, the forces holding individual atoms together, the electromagnetic force binding electrons to nuclei, the strong and weak nuclear forces holding protons and neutrons together. Even these fundamental forces, the very glue of reality, would be overwhelmed. In a terrifying, visceral POV sequence, you would see the ground beneath your feet begin to crack, not from an earthquake, but from the very space between its molecules expanding. Your body would stretch, distort, lengthen, as the cosmic balloon inflates so violently that the ink patterns of you are torn apart, atom by atom. The bonds holding your cells, your molecules, your very atoms together would simply cease to exist. You would be atomized, your constituent particles scattered and accelerated away from each other, each one an isolated speck in an infinitely expanding, utterly empty cosmos. The Big Rip is a scenario where the universe doesn't just die, it's violently shredded. It's a cosmic execution, swift and absolute, leaving behind no trace of structure, no memory of what once was. It's the ultimate annihilation, a tearing apart of existence itself, right down to the fundamental particles. The sound of this universe dying wouldn't be silence. It would be a terrifying, deafening crescendo of tearing, a cosmic shriek as the very fabric of reality is rent asunder. But what if dark energy isn't as dominant as we think? What if, instead of accelerating forever, the universe's expansion eventually slows down, pauses, and then reverses? This brings us to our second violent alternative, the Big Crunch. For a long time, before the discovery of accelerating expansion, the Big Crunch was actually considered one of the most likely fates for our universe. It's an elegant, almost poetic symmetry to the Big Bang. If everything started from an infinitely dense, hot point, a singularity, then perhaps it's destined to return to one. Let's go back to our cosmic balloon. In the Big Crunch scenario, the initial inflation, the expansion of the universe, eventually runs out of steam. Think of blowing up that balloon, but then you stop, and the air starts slowly leaking out, or an invisible hand starts to squeeze it. Gravity, that persistent, relentless force that pulls everything together, would eventually win the cosmic tug-of-war against expansion. The universe would stop expanding, reaching a maximum size, a cosmic peak. And then, slowly at first, but with increasing speed, it would begin to contract. All those galaxies that had been flying away from each other for billions of years would now start to fall back in. The cosmic clock would effectively run backward. As the universe shrinks, everything would get closer. Galaxies would rush towards each other, eventually colliding in spectacular, fiery displays. Star systems would be disrupted, stars would be flung out, and the space between everything would compress. The cosmic microwave background radiation, that faint echo of the Big Bang that permeates the universe today, would become hotter and hotter, brighter and brighter, as the universe effectively unwinds, returning to its initial, fiery state. Imagine the night sky not growing emptier, but filling with light. First, distant galaxies would appear to rush towards us, their light shifting from red to blue as they approach. Then they would collide, merging into supergalaxies, their stars igniting in brilliant bursts of fusion. The sky would become a blinding inferno, hotter than anything we can imagine, as all the matter and energy in the universe are squeezed back into an ever smaller volume. The Big Crunch would be the ultimate implosion. All the black holes, which in the heat-death scenario would slowly evaporate, would here collide and merge, growing into unimaginably massive, super-duper black holes, eventually engulfing everything. The temperature would soar, reaching levels that would vaporize stars, then planets, then atoms, breaking everything down into a plasma of fundamental particles. The pressure would become immense, crushing everything. Space-time itself would warp and distort, becoming incredibly curved and dense. All the structures, all the information, all the intricate complexity that took billions of years to build would be undone, annihilated in a cosmic crush. The universe would collapse back in on itself, returning to a single, infinitesimal point of infinite density and temperature. A final singularity, mirroring the one from which it was born. This idea of a universe that expands and then contracts has a long history. In the 1920s, brilliant minds like Russian mathematician Alexander Friedmann and Belgian priest and physicist Georges Lemaitre, working with Einstein's equations, developed the first theoretical models for a dynamic, expanding universe. Friedmann's solutions in particular showed that the universe could either expand forever or eventually recollapse. Lemaitre even proposed the idea of a primeval atom, from which everything originated, a concept that later became known as the Big Bang. Then, in 1929, Edwin Hubble, that legendary American astronomer, provided the observational proof we needed. He showed that galaxies were indeed moving away from us, and the farther away they were, the faster they were receding. This confirmed the expanding universe model and set the stage for our modern cosmology. For decades, the debate raged. Would gravity ultimately triumph, leading to a big crunch, or would the expansion continue forever, leading to a heat death? The discovery of dark energy and the accelerating expansion in 1998 largely shifted the scientific consensus away from the Big Crunch. It made it seem far less likely, as the repulsive force of dark energy appeared to be winning the cosmic battle. But it's important to remember that science is always evolving. The Big Crunch remains a theoretical possibility if, for example, dark energy isn't constant, or if our understanding of gravity on cosmic scales is incomplete, or if its behavior changes dramatically in the distant future. It's a testament to the open-ended nature of scientific inquiry that even the most well-established theories are constantly being tested and refined. So, here's the aha moment, the core truth that ties these dramatic cosmic farewells together. Our universe's ultimate fate is not a settled fact, not a closed book. It's an ongoing, profound mystery that scientists are desperately trying to solve. And it all hinges on a single crucial number, a cosmic variable that describes the mysterious nature of dark energy. This number, known as W, the equation of state for dark energy, dictates how dark energy behaves over time. If W is exactly 1, then dark energy is constant, and the universe is headed for a heat death. If W is less than 1, then dark energy grows stronger over time, leading to the terrifying Big Rip, If W is greater than 1 but still negative, then dark energy's influence could wane, allowing gravity to eventually dominate and pull everything back into a big crunch. Scientists around the world are poring over data from distant supernovae, from the cosmic microwave background, from the large-scale structure of the universe, all trying to precisely measure this W. It's an incredibly challenging task, fraught with the Hubble tension, a persistent discrepancy in measurements of the universe's expansion rate, which only underscores how much more there is to learn. The slightest variation in this number could mean the difference between an eternal cold silence, a violent atom-shredding tear, or a fiery, crushing collapse. These aren't just abstract equations on a chalkboard. These are potential destinies for everything that has ever existed and everything that ever will. The cosmos could end in a peaceful, eternal fade, a violent, structure-shattering tear, or a fiery, all-consuming collapse. And the fact that we, these tiny, fragile beings on a small blue planet, can even conceive of these possibilities, can use our intellect to gaze into the deep future and imagine the universe's final moments, is nothing short of miraculous. It makes you wonder, doesn't it? If the universe is destined for such a dramatic, ultimate conclusion, whether it's a whisper or a scream, what does it mean for our brief, shining moment within it? What does it mean that we are here now, in this vibrant, improbable instant when the universe is alive, thriving, and through us, aware of itself? These violent alternatives don't just present a different ending. They amplify the preciousness of our present, turning our existence into an even more improbable, more magnificent phenomenon. They make the now not just a gift, but a defiance of the impending ultimate silence. It is a profound appreciation that transcends fear, transforming it into wonder. This journey through the potential endings of everything is not meant to instill despair. Far from it. Instead, it's an invitation to a deeper understanding, a wider perspective. It's an opportunity to appreciate the sheer, breathtaking audacity of existence, the fleeting, beautiful improbability of everything we know and love. Because even if the universe is headed for a tear or a crush, we are here, in this incredible, vibrant middle act, experiencing the most spectacular show imaginable. We are witnesses, and in that, there is an unparalleled privilege. But what if there's another kind of ending entirely? One that doesn't involve the slow, majestic fade of stars, or the dramatic cosmic ballet of tearing galaxies, or gravitational collapse. What if the universe, our universe, exists in a state so fundamentally precarious that its ultimate farewell could come without so much as a whisper of warning, erasing everything in an instant? This is where we venture into one of the most unsettling, yet scientifically plausible, wild card scenarios for the end of all things. The terrifying possibility of false vacuum decay. Imagine for a moment that our entire universe, everything we see, touch, and know, isn't resting on the most solid ground possible. Instead, picture it as a vast, exquisite bubble, delicately perched on a fragile sheet of cosmic ice. This isn't just a poetic image. It's a way to wrap our minds around a concept known as a false vacuum. In physics, the term vacuum doesn't just mean empty space. It refers to the lowest possible energy state of a particular field. Think of it like a valley. A true vacuum would be the absolute lowest point in that valley, where a ball, if placed there, would finally come to rest, unable to roll any further down. It's the ultimate, most stable state of minimum energy. But what if our universe, the very fabric of spacetime and the fields that govern it, isn't quite at the bottom of its valley? What if it's currently resting in a sort of divot, a slightly higher but still stable dip on the hillside? This is the essence of a false vacuum, a metastable state, stable for now, but not the most stable it could possibly be. For decades, physicists have grappled with this idea, especially when considering the Higgs field. The Higgs field permeates all of space and gives elementary particles their mass. Its current energy state, the one we live in, is what we consider our vacuum. But certain theoretical calculations, particularly those that try to unify all the fundamental forces of nature, hint at the unsettling possibility that our vacuum might not be the true vacuum after all. It might just be a false one. So if our universe is like a delicate bubble existing on a sheet of fragile ice, what happens if that ice sheet isn't perfectly stable? What if, at any given moment, a tiny crack could form? This isn't a crack in a physical sense, but a quantum fluctuation, a microscopic ripple in the very fabric of reality that could suddenly transition a tiny region of space from its current false vacuum state to a more stable, true vacuum state. This spontaneous creation of a bubble of true vacuum is the heart of false vacuum decay. This isn't something that would happen predictably, like the slow cooling of the universe or the gradual stretching of space. No. This would be a quantum tunneling event, a phenomenon where a system can spontaneously jump from one energy state to another, even if it doesn't have enough energy to classically overcome the barrier between them. So it's like a ball magically appearing on the other side of a hill without ever having rolled over it. It's weird, it's quantum, and it's utterly unpredictable. It could happen anywhere in the universe, at any time, without warning. And here's where the aha moment truly hits you. A moment that redefines everything we've talked about so far regarding cosmic endings. Because once this tiny bubble of true vacuum forms, it doesn't just sit there. Oh no. That bubble would immediately begin to expand. And it wouldn't just expand. It would expand outwards in all directions, at the absolute maximum speed, allowed by the laws of physics, the speed of light. Imagine that crack in the ice, not slowly spreading, but exploding outwards, instantly converting everything it touches. As this bubble of true vacuum expands, it fundamentally alters the very nature of reality within its boundaries. Think about that for a second. Everything inside that expanding sphere would cease to exist as we know it. All the fundamental constants, the very rules that govern how matter and energy interact, would be different. The strong nuclear force that binds atomic nuclei, the weak force involved in radioactive decay, the electromagnetic force that gives us light and holds atoms together, even gravity itself, all of them could be dramatically changed, or perhaps even cease to function in a recognizable way. What would that mean for you, for me, for our planet, our sun, our galaxy, and every single star and nebula we've ever observed? It would mean instant, absolute annihilation. Not a slow decay, not a tearing apart, not a crushing collapse. Just gone. The moment the edge of that bubble reached you, your atoms, the very particles that make up your body, would find themselves in a universe governed by entirely different rules. They would instantly reconfigure, or perhaps simply dissipate, into something unrecognizable. The universe you knew would be replaced by a different reality, one where the laws of physics that allowed for life, for stars, for galaxies, simply don't apply. There would be no time to see it coming. No faint glow on the horizon. No shifting gravitational anomalies. Light itself, traveling at the universe's ultimate speed limit, would be consumed by the advancing bubble front. If such a bubble were to nucleate right now, a light year away, we would have no way of knowing until it was already upon us, transforming us faster than we could even perceive it. It would be the ultimate, silent, and instantaneous cosmic farewell. This isn't science fiction pulled from a fantastical realm. It's a theoretical, but serious, possibility, discussed by some of the brightest minds in physics. The universe might simply be unstable. And if it is, that instability could manifest at any moment, without any external trigger that we could ever foresee. The bubble of nothing, as it's sometimes called, because it would replace our something with a fundamentally different something that might as well be nothing to us, could be forming right now, light years away, and we would never know until it was too late. This isn't about the universe running out of fuel, or gravity winning, or dark energy tearing things apart. This is about a fundamental flaw in the fabric of existence itself, a cosmic Achilles heel. It's a possibility that underscores the incredible, almost miraculous stability we currently experience. The fact that the universe has existed for 13.8 billion years without this catastrophic event occurring is, in itself, a profound testament to some underlying stability, or perhaps just sheer cosmic luck. The thought of such an ending changes the narrative completely, doesn't it? We spend so much time contemplating the unimaginably vast timescales of heat death, the cosmic violence of the Big Rip, or the finality of the Big Crunch. These are events that unfold over billions, trillions, even googles of years. They give us a sense of cosmic grandeur, a long, drawn-out epic. But false vacuum decay rips that sense of a long future away. It posits an end that is not majestic in its slow decline, or dramatic in its grand collision, but terrifying in its sudden, unannounced finality. It forces us to confront a different kind of fragility. Not the fragility of life on a single planet, threatened by asteroids or climate change, but the fragility of the entire cosmic stage. The very rules of the game could change, and there would be no game left for us to play. It's a profound thought that makes the present moment, this specific configuration of physical laws that allows us to exist, to think, to wonder, even more precious. Because if the universe is indeed a metastable state, a false vacuum, then our existence is not just improbable in its formation, but also incredibly fortunate in its continuation. Every second that passes, every star that shines, every thought that forms in your mind is a moment in a cosmic lottery where the grand prize is simply being. The universe is holding its breath, and so, in a way, are we. This isn't a story of fear, though the implications are undeniably chilling. Instead, it's a story of ultimate perspective. It's a reminder that even the most fundamental aspects of our reality, the laws of physics, the very structure of spacetime, might be temporary. It means that our current now isn't just a brief, shining moment in a long cosmic epic. It's a moment that could be interrupted, utterly transformed, without the slightest warning. And in that realization, there is a strange kind of liberation. If the end could truly be so sudden, so absolute, then clinging to permanence or fearing eventual decay seems almost beside the point. What matters then is the experience of this current reality, the wonder of discovery, the beauty of connection, the sheer miracle of consciousness in a universe that, at its deepest level, might be teetering on the edge of an entirely different existence. The bubble of nothing serves as the ultimate cosmic reminder to live fully within the bubble of our own vibrant, improbable reality, while it lasts. And that brings us, in a very real sense, to our shore, to this moment, to you. We've journeyed through cosmic beginnings, marveled at the birth of light, and stared into the abyss of possible endings, from the slow, cold fade of heat death to the violent cosmic shredding of the Big Rip, and even the terrifying thought of a sudden vacuum decay. Each scenario, in its own way, is a profound reminder of impermanence. But here's the thing about impermanence. It's not just a harbinger of loss. It's also the very wellspring of preciousness. Think of it this way. Our universe, in its entirety, is like an infinite dark ocean of time. An ocean stretching back into an eternal past of nothingness before the Big Bang, and forward into an eternal future of cold, empty void after the last star dies. And in this vast, inky expanse, a truly miraculous thing has happened. A tiny temporary island has emerged, an island of warmth, of light, of structure, of incredible complexity. This is our era, the era of stars, planets, and life. This is our improbable shore. We, you and I, are the lucky inhabitants of this island. We're here at a moment when the universe is alive, vibrant, and incredibly intricate. It's an era defined by the blazing furnaces of stars, the swirling majesty of galaxies, the quiet dance of planets, and the astonishing emergence of consciousness, our consciousness, that can look out at all of it and ask, why, and how, and what next? Now, I know what you might be thinking. If this island is so temporary, if it's destined to be swallowed back by that infinite dark ocean, doesn't that make it all meaningless? Doesn't the knowledge of an ultimate, inescapable end cast a shadow over everything we build, everything we love, everything we strive for? It's a natural, deeply human question. It's the existential dread that whispers in the quiet moments. But what if the answer is the exact opposite? What if knowing the end doesn't diminish our present, but elevates it to an almost unbearable, profound significance? Let's re-anchor ourselves for a moment in the most likely scenario for the universe's ultimate farewell, the heat death, or the big freeze. This isn't a dramatic explosion or a sudden collapse. It's a long, slow, inexorable fade to black. Imagine for a moment an infinite canvas gradually losing all its color, all its vibrancy, until only a uniform cold gray remains. That's the cosmic forecast for our universe, driven by the relentless, accelerating expansion that began roughly 5 billion years ago. It's a process where dark energy, that mysterious repulsive force, making up an estimated 68 to 70% of the total mass energy content of the universe, is the primary antagonist, pushing everything apart, slowly but surely, towards ultimate solitude and stillness. We saw how scientists like Alexander Friedman, in 1922, first gave us the mathematical tools to even conceive of an expanding universe, followed by Georges Lemaitre's primeval atom idea in 1927, and then Edwin Hubble's revolutionary observations in 1929, which showed us, unequivocally, that galaxies were indeed rushing away from each other. But it was the discovery of the universe's accelerated expansion in 1998 by two independent teams of astronomers, a finding that earned their leaders the 2011 Nobel Prize in Physics, that truly cemented the heat death as our most probable destiny. This acceleration means space isn't just expanding, it's expanding faster, pushing everything further apart, thinning out the cosmic soup until it's just a cold, lonely broth. In this future, over timescales that are truly unimaginable, the universe will become an ever emptier, ever colder place. Our Milky Way will eventually merge with Andromeda, forming what some call Milkomeda, a final grand galactic waltz before the isolation truly sets in. Then, the stars will begin to die. First, the giants, then the sun-like stars, and finally, after trillions of years, the last sputtering red dwarf stars will burn out. These are the smallest, longest-lived stars, frugal with their fuel. But even they are not eternal. Picture it, the last red dwarf, a tiny ember in an ocean of black, its light dimming, flickering, and then, with a final sigh, extinguishing forever. That moment would truly be the universe's last light, a profound, silent farewell to the age of stellar luminescence. But even then, it won't be truly dark. Not yet, because waiting in the deep cosmic future are the black holes. These gravitational titans, once thought eternal, are themselves subject to decay. Thanks to the brilliant insights of Stephen Hawking, in 1974, we understand that black holes slowly leak energy through a process now known as Hawking radiation. It's a quantum mechanical phenomenon, mind-bending in its implications, suggesting that even the ultimate cosmic devourers are not immune to the universe's slow march towards equilibrium. A solar mass black hole, for instance, is predicted to take an estimated 10^67 years to completely evaporate. Let that number sink in. A 1 followed by 67 zeros. That's a period vastly longer than the current age of the universe. And supermassive black holes, those behemoths at the centers of galaxies, could take an astonishing 100 years, or even 106 years, to finally wink out. Imagine an animated data visualization playing out over a Google of years, showing a supermassive black hole shrinking imperceptibly at first, then faster and faster, culminating in a final brilliant flash of gamma rays. The universe's last major event, a final cosmic exclamation point before an eternity of silence. And even after the black holes are gone, the universe might have one more trick up its sleeve. The very protons that make up all the matter we know. You, me, the chair you're sitting on, the planet Earth, might not be stable forever. Some grand unified theories predict a hypothetical process called proton decay, where protons would eventually break down into lighter subatomic particles. While never observed, and with a theoretical half-life constrained to at least 67x10^34 years, if this theory holds true, then eventually all matter as we know it would dissolve, leaving behind nothing but a thin, cold soup of photons, electrons, and neutrinos. This is the ultimate, but wait, it gets emptier moment, the final dissolution of all structure. So, the future, in its most probable form, is one of profound, ultimate emptiness. A universe of near absolute zero temperature, where the distances between the last few particles are so vast that they effectively never interact. A universe where information itself, the very memory of what was, might eventually be erased. The sound of this universe dying would be an ultra-low frequency hum, slowly fading into an absolute, perfect silence, a cosmic quietude that stretches into eternity. This is the vast, cold ocean that surrounds our improbable island. It is the overwhelming backdrop against which our brief moment shines. And this is precisely where the aha moment truly crystallizes. The knowledge of this ultimate end does not make our lives meaningless. In fact, it makes this brief, shining moment, this improbable instant, when the universe is alive, vibrant, and, through us, aware of itself, the most valuable and precious thing in all of cosmic history. We spend our lives, as individuals, fighting against endings. We cling to youth, to love, to success, to life itself. We build legacies, hoping for some fragment of ourselves to endure. But what if the end is the most natural thing in the universe? What if, after trillions of years of light and life and fury, the final act of the cosmos is not a bang, but a long, slow, and profoundly beautiful fade to black? This perspective shift is everything. It transforms potential despair into profound appreciation. Consider the alternative, the violent alternatives we explored. What if the universe succumbed to the Big Rip, where the accelerating expansion of space becomes so violent it tears apart galaxies, stars, planets, and even the very atoms that compose us? Or what about the Big Crunch, where gravity eventually wins the cosmic tug of war and the universe collapses back in on itself into a final, infinitely dense singularity. But even if our island were to be violently shattered or crushed rather than slowly eroded, the principle remains. Our existence now, in this particular cosmic configuration, is a fleeting wonder. It's the unique conditions of our current universe, the precise balance of forces, the emergence of stars to forge heavy elements, the formation of planets, the cooling of cosmic microwave background radiation to allow for structure that make life and consciousness possible. These conditions are temporary, a sweet spot in cosmic history. We are quite literally living in the Goldilocks era of the universe, where everything is just right for complex structures to exist. This isn't just about human life, though that's certainly a part of it. It's about the universe itself being vibrant and alive. The fact that galaxies exist, that stars burn, that black holes feed, that planets orbit, all of it is a temporary phenomenon. It's a magnificent, a grand spectacle that has a finite runtime, and we are here to witness it. We are the improbable observers, the brief, shining moments of awareness that the universe has produced to marvel at itself. This perspective doesn't diminish the human quest for knowledge, for beauty, for connection. Instead, it imbues it with an even deeper, more urgent meaning. If the ultimate legacy of the universe is not permanence, but experience, then every moment of wonder, every act of creation, every bond of love, every discovery that expands our understanding becomes an infinitely valuable contribution to that cosmic experience. We are not fighting against the inevitable end. We are participating in the profound, fleeting symphony of existence while it plays. So, look up at the night sky. Those stars you see, those distant galaxies, they are not just points of light. They are the fragile, precious jewels on our cosmic island. They are the evidence of this astonishing temporary flourishing. And you, with your capacity for thought, for emotion, for curiosity, you are the universe's most exquisite, improbable expression of itself right now. This isn't a story of despair. This is a story of profound appreciation. It's a call to embrace the now. This fleeting, improbable instant when the universe is alive and aware of itself through us. We are the universe's brief, incredible conscious moment, a tiny, vibrant island in a sea of cosmic time. And what an honor it is to be here, together, on this improbable shore. We've explored the grandest questions, peered into the deepest abyss of time, and confronted the ultimate end. We've seen that the universe's final chapter, whatever it may be, is not a reason for fear, but for an even deeper reverence for the present. But if our universe is merely one possible iteration, a temporary island in an unimaginable ocean of time, does that mean there are other islands, other oceans? And if so, what lies beyond our own cosmic farewell? If you found yourself awestruck by these cosmic enigmas, if you felt that deep human resonance with the universe's ultimate story, then join us on our next journey. Don't miss out on what comes next from Celestial Enigmas. Hit that subscribe button and become part of our growing community as we continue to explore the universe's most profound secrets together. Thank you for being here on this improbable shore with us. We've gazed into the vast, silent chasms of cosmic time, tracing the universe's grand narrative from its explosive birth to its potential far-flung demise. We've wrestled with the chilling beauty of the heat death, where stars flicker out like distant campfires and black holes slowly, majestically evaporate over timescales that defy human comprehension. We've shuddered at the thought of the Big Rip, where the very fabric of existence is torn apart, or contemplated the crushing finality of a Big Crunch. These are not just scientific theories. They are the universe's own epic poems, whispered across billions of years. But after all this, after we've mentally journeyed to the absolute precipice of everything, a profound question lingers, one that echoes in the deepest chambers of our conscious minds. We spend our lives fighting against endings, don't we? Against the last page of a favorite book, the final scene of a beloved movie, the closing notes of a cherished song. We cling to permanence, to the idea that what is will always be. But what if the end is the most natural thing in the universe? What if, after trillions of years of light and life and fury, the final act of the cosmos is not a bang, but a long, slow, and profoundly beautiful fade to black? We've considered the physical end, the ultimate dispersal of energy, the dissolution of matter itself. But what if something else, something intangible, could endure? What if, in the face of ultimate oblivion, there's an echo, a whisper, a story that persists even after the last star has died and the final black hole has dissolved into a brilliant, fleeting flash of gamma rays? This is where the story gets truly interesting, where the scientific gives way to the profoundly philosophical. Because if our universe, in all its astonishing complexity, is destined for a physical end, whether it's the quiet sigh of the heat death, the violent shriek of the big rip, or the crushing gasp of the big crunch, then what becomes of the information it contains? What becomes of the intricate patterns, the laws of physics, the very structure of reality that allowed for galaxies to form, for stars to ignite, and for consciousness to bloom on a small blue planet? Imagine, if you will, the universe as an impossibly intricate tapestry, woven with threads of light and gravity, matter and energy. Every particle, every interaction, every star system, every thought you've ever had, it's all a form of information, encoded within this cosmic fabric. When we talk about the heat death, we're talking about the threads slowly unraveling, the colors fading, the patterns dissolving, until there's nothing left but a thin, cold soup of elementary particles spread so thinly across an ever-expanding void that interaction becomes impossible. The universe reaches a state of maximum entropy, where all energy is evenly distributed, and nothing new can ever happen. It's the ultimate equilibrium, a cosmic peace so profound, it's indistinguishable from absolute nothingness. But does information truly vanish, or does it merely transform? This isn't a simple question, and physics itself wrestles with it. The idea of information preservation is a cornerstone of quantum mechanics. Black holes, for instance, were once thought to destroy information forever, gobbling it up without a trace. But Stephen Hawking, whose groundbreaking work in the 1970s revolutionized our understanding of these cosmic behemoths, theorized that black holes aren't entirely black. They slowly leak energy, particle by particle, through what we now call Hawking radiation. This process, while mind-bogglingly slow, a solar mass black hole could take an estimated 10^67 years to completely evaporate, and supermassive black holes could endure for up to 10^160 years, suggests that the information about what fell into the black hole isn't truly lost. It's somehow encoded in the emitted radiation, a cosmic echo sent out into the void. Now, stretch that idea to the entire universe. If all matter eventually dissolves, if protons themselves, the very building blocks of atoms, were to decay into lighter subatomic particles, a hypothetical process predicted by some grand unified theories, with a half-life of at least 1.67 exitenu, 34 years. Then what remains? A universe stripped bare of all its physical grandeur, leaving behind only the ghost of its former self. But even in this desolate future, perhaps the story isn't entirely over. Consider the metaphor of a story whispered into the wind. The physical words, the ink on the page, the sound waves that carry a voice. These are transient. They fade. They scatter. But the story itself, the narrative, the meaning, the information it conveys can persist. It can be remembered, retold, reimagined. Our universe, in its 13.8 billion year journey, has told an incredible story. It started from a singularity, expanded, cooled, forged the first elements, ignited the first stars, built galaxies, and eventually produced complex life, capable of observing and questioning its own existence. This entire cosmic ballet is a staggering amount of information. What if, when the last physical vestiges of our universe have dissipated, when the final proton has decayed, when the ultimate heat death has rendered all activity impossible, that story, that immense tapestry of information, doesn't simply cease to be? What if it's merely encoded in the subtle ripples of spacetime, or in the fundamental constants of physics that allowed this universe to exist in the first place? It's a bold thought, one that pushes the boundaries of our current understanding, but it's a question worth asking. When we talk about the Big Rip, we envision an end so violent, so absolute, that even atoms are torn apart by the accelerating expansion of space. Dark energy, the mysterious repulsive force that makes up approximately 68 to 70% of the total mass energy content of the universe and began driving its accelerated expansion roughly 5 billion years ago, ramps up its relentless push until all forces are overcome. In such a scenario, where nothing remains coherent, it's harder to imagine information persisting. But even then, the laws that governed that violent tearing, the fundamental parameters that dictated its timing and intensity, are themselves a form of information. They are the rules of the game, inscribed into the very fabric of reality. And the big crunch? If gravity were to ultimately win, if the universe were to contract back into an infinitely dense singularity, then all the information of our cosmos would be compressed into an unimaginably small point. Would it be destroyed, or would it be preserved, perhaps as the seed for a new beginning, a new Big Bang, carrying the echoes of what came before? This is the tantalizing idea of a cyclic universe, where endings are merely beginnings in disguise, a cosmic reincarnation where the story is told again and again, with subtle variations each time. The beauty of these cosmic farewells, even the most violent among them, is that they force us to confront our own brief, shining moment. Our consciousness, our ability to observe, to question, to marvel at the universe around us, is an improbable miracle. We are, as Dr. Katie Mack so eloquently puts it, the universe becoming aware of itself. This fleeting instant, this cosmic blink of an eye, when stars are burning brightly, when galaxies are swirling, when life can exist and ponder its origins and its end. That is a moment of profound significance. It is the universe's fleeting awareness, its brief experience of its own glory. So, if the physical universe is destined to dissolve, what is truly worth remembering? What is the legacy of this incredible, improbable story? Perhaps the legacy isn't about permanence, but about the experience itself, the intricate dance of particles that formed you, the light from distant stars that fell upon your eyes, the warmth of the sun, the laughter of a loved one. These are all transient physical events, but the experience of them, the information they encoded into your consciousness, the meaning you derived from them, that is something else entirely. Could it be that the universe, in its ultimate end, leaves behind a kind of ghost? Not a spooky apparition, but a fundamental pattern, an informational blueprint, a whisper of what was, encoded into the very laws that govern existence? We don't have the answers, not yet. But the very act of asking these questions, of reaching out into the cosmic void with our minds, is perhaps the most profound thing we can do. It's our way of bearing witness, of recording the story. Even if only in our collective consciousness, the universe will continue its journey, moving toward whatever ultimate fate awaits it. The last red dwarf stars, those tiny, long-lived embers, will eventually sputter out, billions, even trillions of years from now. The supermassive black holes, once the gravitational anchors of galaxies, will radiate away into nothingness, their final act, a burst of gamma rays that will mark the last major event in a universe grown cold and dark. And if proton decay is a reality, then even the most fundamental building blocks of matter will eventually dissolve, leaving behind an unimaginably dilute soup of light, particles, spread across a truly infinite, silent expanse. It's a future that is almost impossible to grasp. A silence so profound, it would shatter any sense of sound we've ever known. The music of the cosmos, the hum of creation, the roar of the Big Bang, the tearing sound of a big rip, the deafening crescendo of a big crunch, all will eventually fade into an absolute perfect silence. And in that silence, what remains? What if the end is not a period, a definitive stop to the grand cosmic sentence? What if it's not the final word, but a question mark? A profound, open-ended query etched into the very fabric of reality, waiting for an answer from a new iteration, a new beginning, or perhaps simply a reverberation through the infinite silence. A story whispered into the cosmic wind, carried to destinations we cannot yet comprehend. Could something of our universe survive its physical end, even if only as information? A ghostly echo in the void, a blueprint for what came before, ready to influence whatever comes next. In the face of ultimate oblivion, what is truly worth remembering? If you found yourself awestruck by these cosmic enigmas, if you felt that deep human resonance with the universe's ultimate story, then join us on our next journey. Don't miss out on what comes next from Celestial Enigmas. Hit that subscribe button and become part of our growing community as we continue to explore the universe's most profound secrets. Together, thank you for being here on this improbable shore with us.